Hello and welcome to Physics Tips for Cambridge Students YouTube channel. Today we are going to be looking at the topic in the 9702 Physics syllabus, that is the AS component, on deformation of solids. Remember to subscribe to the Physics Tips for Cambridge Students YouTube channel. Hit the bell notification so that you get alerted of any new videos. Without much further ado, please let's get started. We are going to start with the lesson outcomes as usual. In this video, I'm just going to focus on stress and strain up to young modulus. And then I'm going to record the second video, which I will be talking about the elastic and plastic behavior of solids. Here, I'll be looking at the elastic potential energy of materials which are under strain. Now let's get started. Deformation of solids. If you remember from your IGCSE syllabus, we did Hooke's law. Hooke's law states that the tension is directly proportional to the extension, provided the elastic limit is not exceeded. So we could have a tension or we could have a compression as well. So that could be an extension or a compression. And the force versus extension graph is a straight line which passes through the origin, meaning that the force is directly proportional to the extension. So we write T is directly proportional to E, removing the proportionality sign and putting a constant of proportionality K, we have T is equal to KE. Now we know that E is equal to the new length minus the original length. The spring constant is the constant of proportionality, which is a symbol K. It has units of newtons per meter. And the bigger the value of K, the stiffer the spring. If the spring is stretched beyond this elastic limit, it does not regain its initial length when the force applied to it is removed. We are going to talk about springs in parallel and springs in series. Now, when two springs or more have been connected in parallel, as shown here, the stiffness increases, so which means K becomes larger. When springs have been connected in series, the K becomes smaller. So which means here it's going to be difficult in parallel to pull the springs apart. So E becomes smaller. So K becomes large. Here so E becomes larger and K becomes smaller. So in parallel, the extension of each spring is the same. The force needed to stretch P is equal to Kp, that is the spring constant of P times its extension. And the force needed to stretch Q is the force Q, which is equal to the spring constant of Q times its extension. The weight is going to be equal to those two forces, Kp, those two forces Fp and Fq. So which is Kpe plus Kqe. And the K, which is equal to the effective K because of the two in parallel. So Kf effective is equal to Kp plus Kq. The spring constant increases. However, the extension tends to decrease. If the two spring constants are the same, then E halves and K doubles. When we've got springs in series, the tension in each of the spring is the same and equals the weight. So you're going to say the extension is equal to W, which is the weight, over the Kp for that is for P. Then extension Q is equal to W over Kq, the spring constant of Q. So E will be equal to EP plus EQ, and we know that E is equal to the weight over Kp. So weight over Kp plus weight over Kq, which is equal to weight over K effective. So which means K1 over K effective is equal to 1 over Kp plus 1 over Kq. So K decreases. In this example, we are told that they are identical springs. So K is the same. So for the first one, F is equal to Ke. For the second one, we have got K over 2 times E. Then here we've got 2K times E, and then 2K plus, then it's in series with that over that. So it's just like resistors in series. So you first of all solve these. These are like resistors in series. So K plus K, which is 2K, and then we have got product over the sum. So 2K times K over 2K plus K. So 2/3 of K. And then here we are going to have 2 in series, so which is K over 2, then K over 2. Then we add K over 2 plus K over 2 is going to give you K. Moving on to stress, strain, and Young modulus. The extension of a wire depends on other factors besides the extension, e.g. the diameter of the wire, its length, and material from which it is made. A longer wire stretches more than a shorter wire of the same material and diameter when loaded with the same weight, but the extension per unit length is the same. A thicker wire stretches less than a thinner wire of the same material when loaded. Tensile stress is defined as the force per unit area perpendicular to the area. So it's given a symbol sigma, which is tension over cross-sectional area, force over area. And the unit of stress is the Pascal or newtons per square meter. Tensile strain is defined as the ratio of the extension to the original length. So it's going to be extension of original length. Strain is a ratio, so it doesn't have any units. The Young modulus is equal to stress over strain. Now we know stress is force over area. Strain is extension over the original length. So it's going to be equal to FL naught over EA, provided that the limit of proportionality is not exceeded. The unit of Young modulus is pascals. That's the unit of stress, because remember, strain does not have units. Measuring Young modulus. Measuring the Young modulus of a wire, you need the test wire and the reference wire. So the reference wire is connected to the main scale, which is a millimeter scale, and then it is subjected to a load which is fixed. So you don't change this load. So the purpose of the load is just to keep the wire taut. Then the test wire has a vernier scale because the extension is going to be very small. So we want to see how it moves. Vernier scale is a small scale. Then this test wire is going to be subjected to variable loads. So we'll be adding the load and then observing what the new length is. Adding loads, new length is, and then you plot a graph at the end. Thin long wires are used to give a measurable extension and large stress for small loads. The diameter of the wire is measured at several points using a micrometer to get the average value. Suppose we need the diameter, mind you, because we've got an area there. So area is equal to pi d squared over 4. As the load is removed, the results are checked to see if we have not exceeded the elastic limit. Then we plot a graph of stress versus strain. So stress on the y-axis, strain on the x-axis. Gradient will be equal to the Young modulus. So we know that Young modulus is equal to sigma over epsilon, right? And we said sigma is F over A and epsilon is extension over the original length. So if you divide, you invert and multiply, so it's going to be F over A times L naught over E. That's how it is. So it's going to be FL naught over AE. So that's why you have it like that. Now we're going to plot a graph of stress versus strain. Then you're going to find the gradient of that graph. So this is an example. Somebody who has already done the experiment. So with the force, they measure the extension, force, measure the extension, and so forth. And then they going to calculate Young modulus from the graph. The second example says a load of 20 newtons on a wire of diameter 1.0 millimeters produces an extension of 0.1 millimeters. If the length of the wire is 3 meters, calculate the tensile stress and the strain. And then you are asked to find the Young modulus of the metal. So, little one there. Tensile stress, remember we said stress is sigma, which is force over area. And the force is 20 newtons. And the area is pi d squared over 4. Remember we said that area is equal to pi r squared, remember, but r is d over 2. So we say d over 2 squared. That's why we've got pi d squared over 4. This is going to be equal to 20 over pi times d squared. It's 1 over 4. But this is 1 millimeter, so that's 1 times 10 to the power of minus 3 squared over 4. You're going to get 2.5 times 10 to the power of 7. These values are always big values. So of the order of millions to giga. So 2.5 times 10 to the power of 7 pascals. Then the tensile strain is just going to be equal to extension over original length, which is going to be 0.1 times 10 to the power of minus 3 over 3 meters. That gives you 3.3 times 10 to the power of minus 5. Remember, it does not have any units. Then to get the Young modulus, is just going to be equal to sigma over epsilon, which is 2.5 times 10 to the power of positive 7 over 3.3 times 10 to the power of minus 5, which is going to be 7.5 times 10 to the power of 11 pascals. So be careful. Young modulus will be of that order, 10 to the positive 11, 10 to the positive 10, thereabout. So I'm going to end the video here. In the next video, I'm going to be talking about elastic and plastic behavior of solids. Please remember to subscribe to the channel, like, share, and comment as well.